So I just wanted to make a quick video on simulating bulk heterojunction structures in GPVDM. Now, usually when you simulate bulk heterojunction, you collapse the complex 3D structure of the bulk heterojunction down to a 1D effective medium model, and this works very, very well, and it's a fantastic method to simulate these complex OPV devices. But in this video, we're going to not do that and deliberately consider the device as a 3D structure. And this all came from this very nice paper by some very clever mathematicians in Chemnitz. And their paper is called Preconditioning for a Phase Field Model with Application to Morphology of Evolution Organic Semiconductors. And you can download it here, and Martin and friends wrote this, and it's quite a nice read. And you can download it there, and you get this PDF. And I'm not going to pretend that I understand all the maths in it, because it's all very, very complicated stuff, and I am not a mathematician. But the bulk of the paper is if you go down to the picture section, which is always a good way to start reading the paper. They effectively made some bulk heterojunction structures numerically, so they had some structures with some parameters that they used to generate it with their models that produce very, very fine morphologies, like this one here, and some that produce sort of very coarse morphologies, and they could tune what came out of their model with various parameters that I don't understand and therefore won't talk about. But what I did is, after they'd done this, I took some slices through these morphologies and tried to simulate those electrically. So if you go down a bit, you get to this figure here, and so there's three of their morphologies. Now, I didn't attempt to properly simulate the 3D-ness of it. I took 2D slices through it. So here's the sort of complexity one. We've got very, very fine bulk heterojunction. Complexity where it's a bit coarser, and complexity 3 where it's very coarse. So we turned these into 3D meshes, and then we could do 2D drift diffusion simulations and calculate the current voltage curves and charge density and things like that. So I'm just going to talk you through how I did this, or how you can do these simulations in GPVDM. So here's the simulation, and you can get to this from new simulations and morphology. And what we have here effectively is we have a device with 3 layers, so top contact, bottom contact, and some active medium. So we can see that in the layers editor there. And this layer here is a bit special because it's made of 2 materials. It's got this light blue box that you can see. So you can see there's these blue triangles here, and they're outside of this sort of bulk heterojunction red squiggle effectively. So we've got sort of this red material inside the blue material. So I'll just show you that the blue material actually exists by showing that at the moment it's just this mesh is showing, but we'll show it as solid. So that's how the device actually looks. It's sort of a square device. But let's just show the mesh of the. Let's hide that solidness and we can see inside again. So if we look at the mobilities of these 2 materials, electrical parameters, we see that the electron mobility of this sort of invisible layer, so this sort of effectively the gaps between the red, where's it gone, is very, very high, and the hole mobility is very, very low. And then for the polymer, which is what the red's effectively simulating, we've got electron mobility is very low, and the hole mobility is very high. So we've effectively made a bulk heterojunction like this. Now this is I've not played with the band gaps or anything like that. You can do that, or that's sort of more advanced simulations. Effectively, this was a sort of demonstration of concept type simulation. So you can go as complicated as you want with this. So I think, should we run this and see if we get a JV curve out? You can see the photons coming in at the top there, so you can there it's dark, and then you've got the photons coming in. So let's just run this and see what we get out of it. And it takes a bit longer to run the average JV curve simulation because obviously it's all 2D, so it takes a bit of time. Whilst that's running, actually, no, I'll let that finish. There we go. I think it stopped early because the current went quite high. So let's look at the current voltage curve, which is jv.dat. So let's have a look at that. There we go. So that's quite a sensible current voltage curve. So you've got something like 200, I don't know, 160, 170 amps per meter squared, and you've got a VOC of between, I don't know, say 0.57, something like that. So that's quite a sensible curve. And what we can do is we can look in the snapshots folder, and we can look at the generation. So that's G of n, that's the generation rate. Let's plot this as a heat map, and we can see effectively we're modelling it. Oh, it's a bit skewed. Let's change that. My screen's very wide. We're effectively having just electron generation within the polymer. So the electrons and holes. So electrons and holes are both being generated in the polymer. And so you could add excitons to this. You could turn on the exciton solver, but I'm not doing that in this example. And we can then look at effectively the free electrons and free holes that these generate. So let's put in the free electrons, and we can see that we get sort of more complicated distribution, but this is effectively the 2D distribution of electrons that's caused by this photogeneration. And then let's put in the free holes, and let's put that as a heat map as well. And we can see these sort of two distributions effectively overlapping. And now we can look at this as a function of voltage, so let's just make it a bit bigger so we can see it properly. There we go. So this is 0 volts, so we can step up the voltage, and we can effectively see how the electron and hole populations behave as a function of voltage. So you sort of study, I mean, we've not dug into this in detail, but you could study sort of how various morphologies or whatever affect carrier distributions and JSC and all things like that. You could look at were you want to do that. So I think that's that there. A couple more things. So one is to notice the actual sort of the squiggles of the polymer. I don't think that's a technical word, but we'll use that word. Don't quite touch the electron injecting contact. There's a gap there, and I've actually embedded the polymer into the contact. And this is to make sure that there's a good contact between the whole majority electrode and the polymer, and there's a good contact between the electron majority electrode and the bulk heterojunction. The other thing is this shape. So you can actually change this shape. So if you go to edit there, you can change this. So this shape is actually morphology 1. And we've got other morphologies. So we've got morphology 2, for example. Word 1 wants to simulate that. You can make your own structures. So I just want to quickly run through how you can make your own structures. I've written about this in the manual. Where's the manual? Here's the manual. I've written about this in the manual. So this chapter is actually going to be, in the manual, is going to be on effectively the contents of this video, but I've not written it yet. But what I have written in the manual that's on the web already is, if we go to the database section, it talks about the shape database, which is what I'm going to be talking about now. It talks effectively at how you can generate these 3D meshes. So there's quite a lot of text on that there that you probably find useful if my video is not clear enough. So that's under the shape database. So move that aside. So let's just look at how we generate these morphologies. Or how we discretize these morphologies, should I say. I didn't generate them, that was Martin and friends. So if we go to the database tab and we go to shape database, and let's look at morphology and go to, say, the morphology we're using here, which is was1. So this was, let's get rid of that. This was, so this is the 3D structure that we're using for the morphology, and it's a closed object in that it's got it's like a sphere in that it's a closed object that it's got a back. If we go back, it's got a back to it, and it's sort of it's an enclosed object. So that's important varieties I'm not going to describe in the manual. And what we can do is, so if we go to the filters, I actually took, this is Martin's original image, and what I did is I applied a threshold filter to it. I then discretized it, so if you go to edit mesh, where's edit mesh? Ah, there we go. We discretized this shape, so I'm going to just put this on no reduce, and just to show you what happens. So if we now go build mesh, let's get rid of that, build mesh. Effectively discretized this shape using a very, very dense triangular mesh. You can see there's thousands of triangles there, but that's a very, very inefficient way of, you can see there's thousands of triangles in that little thing, I don't know how many there are, but that's a very inefficient way of discretizing any type of object in 3D. Whereas if you try to reduce the number of triangles, because you could imagine, for example, you know, in this white bit, you know, why do we need triangle there, we could probably just reduce this square to say 2 slightly bigger triangles. So there's an algorithm to do that, and it's called the node reduction. So if we do that again with that turned on, go build mesh, you can see here it's taking out triangles. Now we've got 10,000 triangles, and it's removed I think 4,000 triangles. So it's removed now sort of 6,000 triangles, 7,000. So it's trying to reduce this mesh down to a sensible size. And then it does a second pass, see if it can pull any more out, and you can see it's not so efficient the second time. We've probably cut the number of triangles by thousands already, and it does a final pass just to make sure it's done its job and this number staying at 0. Give it a second. It's not very good at estimating the time, but it doesn't matter. And there we go. So that's a much better discretization of our object with far fewer triangles. So what you can do is you can import, using the load image option, you can import your own morphology or whatever. You can also actually, I think you actually paint away things here if you want to do that type of thing. So you can sort of edit it a bit yourself if you feel inclined. So once you've generated this morphology, you just need to go right click here and edit and select which morphology you want to import. So that's it really. I think that's it. I'll write some text in the manual on this after I put up the video, but that should enable anybody to simulate 2D bulk heterojunctions as much as they like. And I'll sort of just end this with you do what you want with this, in that I've only sort of looked at very, very simple simulations, but you could push this and do very, very complex things with jumps in bandgap and exton simulations and stuff like that. I'll just show you where to turn on the exton simulation if you want to. If you just need to click enable excitons there, and then you can start playing with exton lifetimes and stuff if you want to go that way. Anyway, so that's it. Hope you enjoyed the video. Thank you very much for watching. And yeah, thank you. Goodbye.